Namaskara. We will now begin our discussions on Bellman Ford algorithm. So, we are going to work on a graph G which has a vertex set V, edge set E, weight function W, a source function S. We are interested in solving single source shortest path problem. That means we have to find out delta V and parent of V for every vertex V. Towards this we had a mathematical formulation and obtained Bellman equations for the delta values, but they have nonlinearity and circular dependency. Okay, nonlinearity and circular dependencies. These two things made solving the Bellman equation impossible. So, we were looking for an iterative way to solve the Bellman equation and obtain the delta values. Towards that we have introduced the quantities like alpha IV and delta IV, and we are going to iteratively build a solution. We are going to still work towards obtaining the solution for Bellman equation, but then in the same equation we are relating alpha I values, okay, and we have derived Bellman equations for bounded walks and bounded paths. That means there is a bound on the number of edges. This leads to a decreasing sequence leading to the answer we are looking for. So, we have alpha 0 for all vertices, using that alpha 1 for all vertices, and finally we will end up alpha n minus 1 for all vertices. This is an iterative process, and that is what the Bellman and Ford algorithm is going to carry out. Basically, the Bellman and Ford algorithm will keep computing the alpha values. If G has no negative cycles, then whatever we are computing turns out to be delta 0 to delta 1 to delta 2 and so on to delta n minus 1. This computation is valid for any graph, but if this computation is carried out on a graph that has no negative cycle, the computation that we are doing, values we are generating are indeed this. That is because for such a G, alpha I V equal to delta I V for all V. That is the reason why our computational process, or whatever Bellman and Ford is doing, is leading to an answer. Why does it lead to an answer? Delta n minus 1 V is in fact equal to delta V. So, the answer we are looking for is obtained through a method of iterated improvement or successive approximation. So, when we are unable to solve directly, we use the powerful mathematical idea of method of iterated improvement. In our context, the method of iterated improvements are achieved through the alpha values. We will see the details. V is less than or equal to alpha I minus 1 U plus weight of UV. For all edges UV, alpha IV is less than or equal to alpha I minus. Not only this, you also have the following fact: alpha IV is equal to alpha I minus 1 u plus weight of uv for some edge uv. For some edge uv this is also true. That means alpha IV is equal to minimum over u not equal to v of alpha I minus 1 u plus weight of uv. Okay. So, this is the Bellman equation for bounded walks. You can call this as Bellman equations for bounded walks. What we mean by bounded means the number of edges, it is limited. We are considering only the walks with less than or equal to I edges here. That is why these are called bounded walks. In general, a walk can be unbounded, any number of edges can be there, but we are focusing on the walks with the bound on the number of edges, and alpha IV is less than or equal to alpha I minus 1 u plus Vu, and it is this. So, we are not able to solve the Bellman equation for deltas. That is because the Bellman equation for deltas have circular dependency, but you can see that the Bellman equation for the alpha values, they do not have circular dependency. You can smoothly proceed. Look at the dependency. Alpha I is depending on only alpha I minus 1. So, if I have alpha I minus 1 yes, alpha I minus 1 another vertex, alpha I minus 1 yet another vertex, and so on, somewhere alpha I minus 1 u, right, alpha I minus 1 u. I have alpha I values. Using this I can get alpha I values. All alpha I values are depending on alpha I minus 1 values. That means from the values in the array alpha I minus 1, we can by using, let us use the y from, by using the values in the array alpha I minus 1, we can compute the array of values alpha I. It is an array, okay, all values. So, you have n values in alpha minus 1 array, one value for each vertex, and you compute. So, how do we compute this? Here is a very simple pseudo code based on the equation, Bellman equation that we have seen. Okay. Here is the Bellman equation, I will show once again. Okay. Here is the Bellman equation. So, based on this Bellman equation we have to so this is what we are going to do. Every edge has a potential to improve the alpha value of some v, especially uv may improve, right, the value of alpha IV. Therefore, here is the simple plan. Pseudocode to improve, okay, pseudocode to compute alpha I array based on alpha I minus 1 array values. Based on these values, how do I do that? First of all, I will set alpha I V is equal to alpha I minus 1 V, because either it is this value or probably smaller value. Remember, it is a hierarchy. So, the bigger set minimum, either the minimum of the smaller set or it could become smaller. Let us see whether it is becoming smaller. Alpha I equal to V, this is step 1 for all V. First copy the array value alpha IV to alpha I minus 1 V to alpha IV. Then for each edge UV, do it in the next page. So, I will cut this. Computing alpha IV values by using alpha I minus 1 array values. How do we do that? Alpha IV is equal to alpha I minus 1 V for all V belonging to V. This is step 1. And step 2, for each UV in E, for each edge UV in E, if alpha IV is greater than alpha I minus 1 U plus weight of UV, that is, you have found a smaller value. Because you have found a smaller value, you have to update it to the smaller value. That is the way to find the minimum. The way in which we find a minimum is we keep scanning the values. When we find something smaller, you replace with a smaller. Straightforward logic of finding the minimum. If alpha IV is greater than alpha IU plus UV, then alpha IV equal to alpha I minus 1 U plus WUV, and we have to save the Bellman edges. So, the current Bellman edge is the edge UV which is changing the value. We have already seen that we are going to use a convention of previous P array notation, because Bellman edges are always last edges, and in the last edge UV, U is going to be previous to V. Therefore, in this edge UV, therefore previous of V equal to U, this is Bellman edge. This is actually current, we will write it as current Bellman edge. This Bellman edge will get updated. Current Bellman edge. When the loop terminates, alpha I v will have the minimum and P of v will have the previous of the last edge. It will have the Bellman edge, proper Bellman edge ending at v. So, when the loop is terminated, when step 1 and step 2 are done, after this alpha I v will have minimum over, because minimum over u not equal to v of delta u plus weight of u v, sorry, not delta, my apologies, it is alpha I minus 1 alpha I minus 1, every alpha array is fully consulted, wherever there is a u and an edge u v, this value is computed and minimum, the smaller value is updated, therefore it will have the minimum, alpha I will have the minimum and P v v is the Bellman edge ending at v, and P v v is the Bellman edge ending at v. Maybe I will write this cleanly next page, so that I will erase it. This can be edited, one second. So, what is the consequence of executing? The consequence of executing is alpha I v is equal to minimum over u not equal to v of alpha I minus 1 u plus weight of u v. This is the correct value that we want, and P v v is the Bellman edge ending at v. You have a current Bellman edge, but that was updated. Finally, when you finished with alpha I will have the correct value and P v v is the Bellman edge ending at v. So, this is called the improvement step. This is called improvement step. Improvement step. It improves alpha I vector or array of values to alpha I array of values. Alpha I minus 1 array of values. Let us pause a moment to find out what is alpha 0. Okay. Let us see alpha 0 array. What is alpha 0 S? It is the length of the walk from S to S, from S to S with maximum 0 edges, that is no edge at all, maximum number of edge, at most 0 edge means no edge. From S to S you have to go without using an edge, 0. What about alpha 0 V for all other one? From S to V you have to go without using any edge, maximum 0 edge you are allowed. There is no such walk. If there is no such walk, it is infinity. Therefore, this is alpha 0. You know how to compute alpha minus 1 to alpha I. Therefore, use this improvement step n minus 1 times. From alpha 0 array build alpha 1 array, from alpha 1 array build alpha 2 array. In this way you keep building it until you get alpha n minus 1 array. Alpha n minus 1 array you build. How do you go from one array to another array? The improvement step that we have shown. Okay. The improvement step that we have shown here, okay, tells you how to go from alpha I minus 1 to alpha I. Now, so from alpha 0 you go to alpha 1 and you stop here, alpha n minus 1. So, you have alpha n minus 1 vector, that means alpha n minus 1 yes, alpha n minus 1 for another vertex, alpha n minus 1 for yet another vertex. So, in this way you have alpha n minus 1 for all vertices you have. Since G has no negative cycles or 0 cycles, this is nothing but delta n minus 1 yes, delta n minus 1 whatever is that vertex, delta n minus 1, this is nothing but the, because we know that we have already seen that alpha I equal to delta I if G has no negative cycles. But delta n minus 1 is nothing but delta, therefore delta S is computed, delta of this vertex is computed, delta of all vertices are computed. In other words, single source shortest path problem is solved. You can see that when we were trying to find the delta values directly, when we were trying to find the delta values directly using Bellman equation, we were caught in a mess. There was cyclic dependency and we were not able to get it. But now we are getting the delta values in a different way. We are using Bellman like bounds for bounded walks. Those bounded walks have got nice relation which is very easy to compute in one go. You can start from alpha 0 and go to alpha 1, from alpha 1 you can go to alpha 2. So, you are able to go and finally you get alpha n minus 1 for every vertex. Alpha n minus 1 for every vertex is nothing but delta n minus 1 for that vertex. Okay? We have seen that alpha n minus 1 v is nothing but delta n minus 1 v. Delta n minus 1 v is nothing but delta v because no path can have more than. So, you have solved the delta v for all v by taking a slightly different route. Okay? Very impressive, isn't it? You were stuck at a method for finding the delta directly, but we used another method. In that method we have proceeded iteratively and we have reached the delta values through an iterated improvement process. Okay. So, we will this is a right point to break. Thank you.